This is a review of the basics of isotopic age dating, where the discussion turns to isotopes, half-lives, and radioactive decay processes, and how they are used to determine a number age, or absolute age, for certain types of minerals and rocks. Ultimately, both relative and isotopic dating methods are used to create the official geologic timescale and to interpret geologic history. Shown here is an area at Hance Rapid along the Colorado River in the Grand Canyon. The main feature is this dark gray intrusion, which is cutting through this layered reddish rock. The relative dating principle cross-cutting relations would tell us that the gray intrusion is younger than the reddish rocks. It's younger than anything it cuts across. And so that's a relative statement. We don't know how much younger. But as it turns out, this intrusion has certain minerals in it which have certain isotopes that can be dated. And those dates are about 1100 million years. What that means geologically is that this intrusion was once a magma that crystallized 1100 million years ago. That's 1.1 billion years ago. It's a long time ago. Anyway, that's an absolute age. And while we can't directly date the reddish rock, we can indirectly give it an age of greater than 1100 million years when we combine both the absolute age and relative dating. This is an example of how we use both absolute and relative dating to describe the geologic history of an area. Geochronology is the scientific discipline devoted to dating minerals, rocks, and geologic events. Certain isotopes of some elements are unstable and decay over time. Of the over 90 known elements, only a handful have isotopes that are used in dating rocks and minerals. There are many different methods to determine a number age, but only certain radioactive isotopes of some minerals are suitable in providing this information. Additionally, these isotopes, like argon-40, uranium-238, rubidium-87, etc., are only present in certain minerals, which are only present in certain rocks. In other words, not every rock you pick up on a hike will be able to yield a number age. And it is the job of a geologist to know which rocks and minerals to look for and to know the geologic context of any age that's calculated. Isotopic dating measures the decay of radioactive isotopes to date rocks. This type of dating yields specific numerical dates, which are typically interpreted to represent the formation age of a mineral or rock. For example, the isotopic date on the volcanic rocks that cap Tempe Butte on the campus of Arizona State University has been calculated at 17.6 million years. Remember, MA is mega annum, or million years. The measurement error may be included with the age date to show the quality of the data. Here, the volcanic rock is 17.6 plus or minus 0.4 million. That means it could be as old as 18.0 million or as young as 17.2. Fresh samples analyzed with modern techniques usually yield a rather low measurement error. Every element has its own unique number of protons in its nucleus. This is how we distinguish one element from another. For example, the element carbon has 6 protons in its nucleus. Always. If an atom does not have 6 protons in its nucleus, then it isn't the element carbon. However, in any given element, the number of neutrons in the nucleus can vary. These variations of the same element are called isotopes. The element carbon has 3 naturally occurring isotopes: carbon-12, carbon-13, and carbon-14. Each of these carbon isotopes has 6 protons, but differ in the number of neutrons. For example, carbon-12 has 6 protons in its nucleus and 6 neutrons, totaling 12 particles, hence the name carbon-12, typically written with a superscript 12 before the capital letter C for carbon. Carbon-13 has 6 protons and 7 neutrons, totaling 13 particles. Carbon-14 has 6 protons and 8 neutrons, for 14 particles. As it turns out, carbon-12 and carbon-13 are what are called stable isotopes and do not experience radioactive decay, whereas carbon-14 does experience radioactive decay. And although carbon-12 and 13 are useful in other ways, only carbon-14 is unstable and experiences radioactive decay, so it's useful for isotopic dating. Radioactive decay is the process where an original unstable nucleus, the parent, changes form into at least one new nucleus, the daughter, which may or may not be stable. There are several ways in which the decay process occurs, but all involve the release of energy, or radiation, either through the loss of a particle from the nucleus, alpha decay, or the changing of a neutron in the nucleus to a proton, with the resulting emission of an electron, that's beta decay, or the emission of a photon, or gamma ray, that's gamma decay. In this lecture, we will not concern ourselves with the further details of the different decay processes. Radioactive decay humor is always tight. In the radioactive decay process, the amount of parent material decreases over time, and conversely, the amount of daughter material increases over time. In this simple example, we start with all parent atoms, and over time, more daughter atoms accumulate. The rate of decay widely varies between different types of isotopes, from very long periods like billions of years to ultra short periods like much less than a second. There are many parent-daughter isotope pairs that we use in geochronology. The ones listed here are commonly used in geologic age dating applications, and they include samarium-147, neodymium-143, rubidium-87, strontium-87, uranium-238, lead-206, potassium-40, argon-40, argon-40, argon-39, and carbon-14, nitrogen-14. So we need to understand how radioactive isotopes decay before we can use them to date geologic samples. There are several different types of decay processes, with the simplest one being linear decay. And this is where the starting quantity decreases by a fixed amount over equal intervals of time. An example would be the burning of a candle. Before being lit, there is 100% candle present. After the candle is lit, it starts burning down, and after a certain period of time, say 1 hour, there is 3/4 of the original left, or 75%. So the candle decayed by 25% in 1 hour. At 2 hours, the candle has burned down to 1/2, or 50%. So the candle lost the same amount, 25%, in the second hour as it did in the first hour. After 3 hours, the candle is burned down to 1/4, or 25%, and after 4 hours it's burned out with no original candle left. Another analogy is if we start with a full bottle of water and regularly pour out the same amount for every equal period of time, in this case, every 5 seconds. We will quickly have an empty bottle of water. After about 20 seconds. These are both examples of linear decay. Exponential decay is another type of change where the amount of decrease is proportional to the size of the population. Here, the original quantity decreases at a fixed rate at regular intervals. Unlike linear decay, the amount of decay is not fixed, but is very rapid at first and then slows down. Let's use the water bottle analogy again, but this time for exponential decay. We start with a full bottle of water, with the water representing the amount of radioactive parent isotope. After a certain amount of time, again let's do every 5 seconds, we will pour out half or 50% of the amount in the bottle that we started that interval with. So after the first 5 seconds, we pour out half of the full water bottle, leaving us with a half-full water bottle. During the next 5-second interval, we will pour out half of the half-full water bottle because the fixed rate of change is 50%, leaving us with a quarter-full water bottle. During the next 5-second interval, we pour out half of the quarter-full water bottle to get a 1/8 full water bottle. Notice that the rate of change is fixed, but the amount of change is not. It's actually decreasing. For the next 5-second interval, we get down to 1/16 full, and so on and so on and so on. Thus, in exponential decay, although the amount of water is quickly reduced, it takes a longer length of time to run out as compared to linear decay. The rate of change is constant, 50% per time interval, but the amount of change is not. It actually decreases with time. Since the early 20th century, measurement of various radioactive isotopes has shown that they decay in an exponential manner, and these diagrams graphically display this. The amount of parent isotope decreases exponentially with time, with a concurrent increase in the amount of daughter isotope. The diagram at right shows how the parent-daughter isotope ratio changes as decay progresses with time. Start with lots of parent, exponentially decreasing to very little. Start with little or no daughter, and it increases over time at the expense of the parent. The parent-daughter ratio is shown here. Again, when you have all parent, the parent-daughter ratio is very high, and with time, this ratio decreases until there's an even amount, a 1-to-1 ratio, and then eventually there's much more daughter than parent, so the parent-daughter ratio becomes very small. Each type of radioactive parent isotope has been shown to decay at a particular rate, and these rates of decay have all been proven to be constant. For any given radioactive parent isotope, the time it takes for half of the parent to decay into daughter atoms is called the half-life, which is typically denoted by the Greek letter lambda. This diagram shows the percentage of parent isotope relative to the number of half-lives that have elapsed during the radioactive decay process. At the beginning, 0 half-lives, there's 100% parent material in the mineral. And as decay progresses, more and more daughter isotope build up at the expense of the parent isotope. The time it takes for 50% of the parent to decay into daughter is considered a half-life. This period of time could be less than a second, it could be an hour, it could be a year, 1,000 years, a million years, a billion years, or more. So knowing the half-life of any given radioactive isotope is incredibly important in calculating the absolute age of any rock sample. And of course, Gordon Freeman will tell us that Half-Life is one of the best video games of all time. Isotopes with long half-lives decay very slowly and are useful for dating older rocks, like millions or billions of years old. The half-life of potassium-40, for example, is about 1.3 billion years. Remember, Ga is gigaannum, or billion years. The half-life for uranium-238 is a little bit more at 4.5 billion. The half-life for samarium-147 is a whopping 106 billion years. These are extraordinarily long periods of time. How do we know these numbers are real, that we didn't just pull them out of thin air? Well, we didn't just make them up. Since we discovered radioactivity over 100 years ago, we've been measuring the rates of decay of various isotopes, and even for the very long half-life isotopes, there is some measurable amount of decay that we can extrapolate and come up with these half-life numbers. Let's look at an example of the decay of potassium-40 into argon-40. At the beginning of the radioactive decay process, we have 100% parent material. So 100% of the isotopes are potassium-40. 0% are argon-40. So this is 0 half-lives. With time now, the amount of parent material will decrease and the amount of daughter material will increase. After 1.25 billion years, we are down to 50% parent material. So we've decreased from the original amount by half. This is the definition of a half-life. So 1.25 billion is the half-life for potassium-40. The amount of daughter material has increased to 50%, and so the parent-daughter ratio after one half-life is 1 to 1. After another half-life, 2.5 billion years down the line, we're down to half of 50%, 25% parent, and the amount of daughter has increased to 75%. And this yields a parent-daughter ratio of 1 to 3. After 3 half-lives, or 3.75 billion years, we're down to half of 25%, or 12.5% parent, and almost 88% daughter, for a 1 to 7 parent-daughter ratio. And after 4 half-lives of decay, 5 billion years have gone by, and we're down to a little more than 6% of the original parent isotope, potassium-40, and we've built up almost 94% of the daughter, argon-40. So you can see that due to its long half-life, potassium-40 is good for dating rocks that are millions or even billions of years old. Isotopes with short half-lives decay very quickly and are useful for dating younger rocks, say thousands or millions of years old. The half-life of carbon-14 is only 5,730 years. This is relatively short compared to the long half-life of potassium-40, 1.25 billion years. Let's review an example for the decay of carbon-14 into nitrogen-14. At the beginning of the decay process, we have 100% parent, carbon-14, and 0% daughter, the nitrogen-14. As decay progresses, we have more and more carbon-14 transforming into nitrogen-14. After 5,730 years, we're down to 50% parent. So this is one half-life for carbon-14. 50% parent, 50% daughter, a 1 to 1 parent-daughter ratio. 2 half-lives, or 11,460 years after the start, we're down to 25% parent, 75% daughter. 3 half-lives is 17,190 years later. Okay, so we're down to 12.5% parent and almost 88% daughter. Fast forward to 7 half-lives later. This is roughly 40,000 years after the beginning of the decay process, and we are down to less than 1% of the original parent material. So, due to its short half-life, carbon-14 is good for dating carbon-rich material that is younger than, say, 50,000 years old or so. In a lab, we can measure the amount of parent and daughter and express it as the parent-daughter ratio. This is done with a device called a mass spectrometer, which is able to distinguish different types of isotopes. The parent-daughter ratio, as we've seen, is a clue to how far the decay process has progressed. Let's look at a graph of a hypothetical decay process. Here we have parent isotope in blue, daughter isotope in red. At the beginning of the decay process, we have 100% parent, of course, and 0% daughter. This yields a parent-daughter ratio that's undefined. With time, we will have less parent and more daughter. At some point, we will have 75% parent, 25% daughter. That would have a parent-daughter ratio of 3 parts parent, 1 part daughter, or 3 to 1. With continuing decay, we'll get to the point where there's 50% parent, 50% daughter. This would be a 1 to 1 parent-daughter ratio. Still later, there's now less parent and more daughter, and at some point we might have 25% parent, 75% daughter. And this would be a parent-daughter ratio of 1 part parent, 3 parts daughter, or 1 to 3. Decay will continue out indefinitely, with less and less parent and more daughter, and so this will yield increasingly smaller and smaller parent-daughter ratios. Comparing the parent-daughter ratio of a given parent-daughter isotope pair can be useful in determining relative age of different rock samples. We know that lower ratios are due to less parent and more daughter, resulting from more radioactive decay, and thus older rocks. Whereas higher ratios are from more parent and less daughter, and this is representative of less radioactive decay in younger rocks. Here's a simple example. In rock sample A, we measured roughly 3 times as much daughter isotope as parent isotope. This yields a parent-daughter ratio of 1:3. In rock sample B, we measured roughly twice as much parent as daughter isotope. This gives us a parent-daughter ratio of 2:1. Since we measured the same type of parent and daughter isotopes in each sample, we can conclude that sample A is older than sample B because it has a lower parent-to-daughter ratio. Lower parent-to-daughter ratios reflect more decay time and thus older rocks, and higher parent-to-daughter ratios reflect less decay time and thus younger rocks. Note that by itself, the parent-daughter ratio does not give us a number age. For that, we need to know the rate of decay, or the half-life. In geochronology, the radioactive decay process is interpreted as if it were some kind of atomic clock that can reveal the length of time in which the decay process occurred. Consider a magma with different types of isotopes in it, some stable and some radioactive. This situation is represented by the panel at left here. As the magma cools, atoms start to form bonds with other atoms and mineral crystals start to form. This would be the center panel. Some crystals may incorporate certain radioactive isotopes, but exclude their daughter atoms. The atomic clock starts ticking once the mineral crystal locks in its parent isotopes and consequently locks out any daughter isotopes. Within each mineral crystal, the parent material then decays over time and the daughter material builds up. And this would be the panel at right. So now we know what we need to get a number age. First, we must have a sufficient amount of the appropriate parent and daughter material. From this, we can determine the parent-daughter ratio and infer how many decay cycles or half-lives have occurred. Second, we need to know the half-life of the parent isotope. With this information, it is possible to calculate the isotopic date of the sample. Here's another hypothetical example. Ford and Sandy collected an igneous rock on a hike at South Mountain and want to know its age. They sent the rock off to a lab, and analysis revealed that it has a parent-daughter ratio of 1:3. This ratio represents the passage of 2 parent isotope half-lives. So if the parent isotope half-life is 10 million years, we know the age of the rock is 20 million years. There's actually a lot more involved in the calculation of a number age than this shows, but it is essentially how we get isotopic dates for rock samples. The process of isotopic dating includes a number of important constraints that need to be satisfied in order to get a reliable age date. First of all, an adequate, measurable amount of sample material is needed. Next, the sample must represent a closed system. This means that neither parent nor daughter atoms were either added or removed during the history of the sample. This usually occurs through the process of metamorphism, so we look for signs of weathering or alteration that could mean that the sample has been modified and does not represent a closed system. Another constraint is that the mineral crystal must have originally formed with only parent isotopes and no daughter isotopes present at the beginning. Lastly, the rate of decay for the various isotopes must be constant and measurable. The half-lives of many isotopes have been measured in labs around the world for over 100 years. So what do we need to get an isotopic age date? Ultimately, we will use an isotope with the proper half-life for our dating purposes. And this might be uranium-238 or potassium-40 or argon-40 if we are dating rocks that are millions or billions of years old. If we are dating young carbon-rich material, then carbon-14 is our isotope. A given isotope is typically incorporated into certain minerals. For example, uranium-238 is typically present in the mineral zircon. whereas potassium-40 is common in the mineral muscovite and alkali feldspar. Carbon-14 can be found in unfossilized organic material. These minerals are only present in certain rocks. Many types of igneous rocks include these minerals, but unfossilized organic material is only found in sedimentary rocks. So now we have an isotopic date, but what does it mean? Well, isotopic dates derived from igneous rocks commonly represent a crystallization age, or the time at which the rock cooled and solidified from a lava or magma. For example, an isotopic date from a rock that represents an ancient lava flow or magma intrusion represents the time when the parent isotopes were first locked into their host mineral crystals as the minerals were originally crystallizing. This is known as a crystallization age and represents the true age of the rock. In sedimentary rocks, we are typically dating a clast within the rock. Thus, the isotopic age is the crystallization age of the clast, which is older than the host sedimentary rock. Remember, principle of inclusions. If we are dating carbon-rich organic material, then the date represents when the plant or animal died. Isotopic dates from a metamorphic rock typically do not represent the true age of the rock. Metamorphism is a process that disturbs the closed system parent-daughter isotopic decay by altering the amount of parent and daughter material. However, even though metamorphism alters the atomic clock, the isotopic date can still be meaningful. Consider the example of an igneous rock formed from an ancient lava flow, where the parent isotopes are locked into their host mineral crystal as the rock crystallizes. It's here that the atomic clock starts to tick and daughter isotopes begin to accumulate. The amount of parent isotope decreases and daughter isotope increases as time goes on, and at some point the rock may be subjected to metamorphism, possibly from plate tectonic activity. The migration of metamorphic fluids through the crystal results in the loss of daughter isotopes, and afterwards the parent-daughter decay resumes as normal. So if we date the mineral crystal from panel 4, we will measure a parent-daughter ratio that has been modified and does not represent the true crystallization age of the rock. The rock will appear younger than its true age because of the loss of daughter material during metamorphism. It should be noted that if metamorphism removes all of the daughter isotope material from a mineral crystal, as in panel 3, then it effectively resets the atomic clock to 0. In this case, the isotopic age will represent the time of metamorphism, not the time the rock formed. This can actually be a very important aspect in the study of mountain building processes and plate tectonics. Combined with various relative dating principles, isotopic dates can indirectly provide age information on surrounding rock layers, some of which might not be isotopically datable. Consider this example, where we have two lava flows, which are datable using isotopic methods, bracketing a carbonate unit or limestone, which typically lacks the required isotopes to get an isotopic age. If we determine that the lower flow is 400,000 years old and the upper flow is 200,000 years old, then we know the age of the limestone must be somewhere in between 200 and 400,000 years old. This seems incredibly simple, but it's actually very powerful in dating rocks that we can't otherwise date with isotopic methods. The official geologic timescale is a dual scale based on the relative ages of rock sequences around the world, with isotopic age dates added to it. And this has been constructed over the last 100 years or so. Occasionally, some of the boundary dates may change slightly as new stratigraphic information is discovered, or analytical techniques are improved. Click on the book link to learn more about this chart and get the latest version. Previously, we deciphered the relative order of the units in this geologic sequence diagram. Now we have isotopic dates for the three igneous units, the sill D, the dike F, and lava flow H. From our previous work, we determined that Unit A is the oldest, then B, and then C, and that was from superposition. Those were followed by unit E, then the sill D, using inclusions. The dike F is next, that's from cross-cutting relations, followed by the remaining sequence of units G, H, I, J, and K, and that's simply superposition. Now, because we know the exact ages of the three dated igneous units, D, F, and H, we have indirect age information on the other units as well. If the age of the sill D is 100 million, then the sedimentary layers A through E are all older than 100 million. The age of layer G must be between 1 million and 10 million, and finally all of the layers above lava flow H must be younger than 1 million years old. We can also date geologic events, like the tilting and erosion that occurred during the time between when unit F intruded at 10 million and when unit H was erupted at 1 million. Thus, the addition of isotopic dating gives us a more specific view on the nature of geologic units, events, and history. This is the list of units from oldest to youngest, with the isotopic age dates added, and then the indirect ages listed as well. Well, that's all for now. Till next time.